Every time we look at the planets in our solar system, science fiction has trained us to imagine impossible speeds. Movies show giant ships crossing billions of kilometers in a matter of hours while astronauts walk calmly through glowing corridors as if deep space were just another international flight. Reality is far less forgiving. Space is enormous beyond human intuition, and even with the most advanced technology humanity has ever built, reaching another world still demands patience measured in months, years, and sometimes decades. The truth is that space travel is not controlled by imagination alone. It is controlled by gravity, fuel mass, orbital mechanics, and the brutal limits of physics. If humanity seriously attempted to visit every planet in the solar system using technology that actually exists or is currently being developed, the timelines would shock most people. A realistic mission cannot simply point toward a planet and fly in a straight line. Every planet is constantly moving around the sun at thousands of kilometers per hour. A spacecraft launched from Earth is already traveling around the sun before its engines even ignite in deep space. To reach another world, scientists must calculate precise orbital transfers that allow the spacecraft to intercept a moving target millions or even billions of kilometers away. This is why mission planners rely heavily on gravity assist and transfer orbits. A spacecraft can swing around a planet and steal some of its momentum like a perfectly timed slingshot. That technique allows probes to gain incredible speed without carrying impossible amounts of fuel. The most common pathway is called a Hohmann transfer orbit, an efficient curved trajectory that minimizes energy use, but dramatically increases travel time. In space, efficiency usually means moving slowly. Speed is expensive, and every extra kilogram of fuel creates another problem during launch. Even propulsion technology has limits that most people underestimate. Chemical rockets remain the backbone of modern spaceflight because they generate enormous thrust during launch, but they consume fuel at terrifying rates. Ion thrusters are far more efficient and can accelerate continuously for months or years, yet their thrust is so weak that they would never feel powerful to a human passenger. Nuclear propulsion systems may eventually shorten these journeys, but most remain experimental concepts rather than operational reality. At least for now, the planets remain staggeringly far away. The first destination people usually assume would be easy is Mercury, because it is the closest planet to the Sun and often appears relatively near Earth on a cosmic scale. Surprisingly, Mercury is one of the hardest worlds to reach. The distance between Earth and Mercury changes constantly, ranging from roughly 77 million kilometers to more than 200 million kilometers. The real difficulty comes from the Sun itself. Mercury races around the Sun at extreme speed, and any spacecraft traveling inward toward it also accelerates because of solar gravity. Without careful braking maneuvers, a probe would simply shoot past the planet. That is exactly why missions to Mercury require complicated gravity assists around Venus and Mercury itself. Instead of flying directly there, spacecraft often loop through the inner solar system multiple times to gradually reduce velocity. The European and Japanese mission called Bepi Colombo is following this strategy right now. Even though Mercury is technically closer to Earth than Mars at certain moments, the travel time can still stretch between 5 and 7 years. Reaching Mercury is less about distance and more about controlling speed and the overwhelming gravity of the Sun. Venus is completely different. At its closest approach, Venus can come within around 38 million kilometers of Earth, making it our nearest planetary neighbor. Under favorable orbital conditions, a robotic mission can arrive there in as little as 3 to 5 months. In terms of travel time alone, Venus is the easiest planet to reach. Soviet Venera probes and later American missions repeatedly demonstrated that relatively quick journeys to Venus are possible with existing technology. Yet Venus hides a nightmare beneath those short travel times. The atmosphere is dense enough to crush machinery. The surface temperature is hot enough to melt lead, and clouds of sulfuric acid surround the planet. A crewed mission could theoretically reach Venus faster than Mars, but surviving near the planet would become the real challenge. Even floating cities proposed for the upper atmosphere remain highly speculative concepts. Then there is Mars, the world that has dominated human imagination for generations. Mars represents the closest thing humanity has to a second home. Even though it remains brutally hostile by Earth standards. Depending on orbital positions, Mars sits between 56 million and more than 400 million kilometers away. The ideal launch opportunity appears roughly every 26 months when Earth and Mars align favorably around the Sun. Nearly every successful Mars mission has depended on these narrow launch windows. Most robotic missions to Mars require 6 to 9 months of travel time using conventional transfer orbits. Curiosity, Perseverance, and several orbiters all followed similar timelines because the laws of orbital mechanics leave little room for shortcuts. A human mission would probably take 8 or 9 months each way unless nuclear propulsion becomes practical. That journey alone would expose astronauts to radiation, isolation, muscle deterioration, and psychological pressure unlike anything experienced on Earth. The larger problem is that astronauts could not immediately return home after landing. Earth and Mars must realign before the return trajectory becomes efficient again. That means a realistic crew would likely remain on Mars for more than 500 days waiting for the next launch opportunity. Add the outbound and return flights together, and the total mission length approaches 3 years. NASA and private companies already designed their long-term plans around these unavoidable windows because physics does not negotiate with ambition. Even with future engines, Mars will never become a quick weekend destination. Every mission will demand preparation, precise timing, and crews willing to spend years living farther from Earth than any humans in history. Beyond Mars, the solar system changes dramatically. Distances become so extreme that even robotic exploration starts turning into multi-decade projects. The gas giants and ice giants are not merely farther away than the inner planets. They exist on a completely different scale of isolation. Signals from Earth can take hours to arrive there. Sunlight becomes weak and cold, and every mission must survive in deep space for years before reaching its target. Jupiter is the first giant barrier. At its closest, Jupiter remains more than 580 million kilometers away from Earth, and at its farthest it approaches nearly 1 billion kilometers. It is the largest planet in the solar system and contains